Morning, Diffie
Hi. Good morning, Doug.
Welcome to Monday. Welcome to week 2. Kim is here from camping.
Morning.
Greetings. Did you find everything in My Open Math, Kim?
I found everything in my open math, except I didn't see any lecture recordings. Are those stored somewhere else, or did I just not look in the right spot?
They're all in class notes.
Okay, got it. Yes, I forgot about that.
Yeah, I put the written stuff first and then the lecture right behind it based on date.
Cool. Okay, I'll catch up on that.
We'll talk. Marvelous. I have to turn on Def Leppard. That's not cool. All right, let's share a screen and start thinking. See if the technology will let us through today. So we're looking at 2.3 today, which is solving linear differential equations. And we just got done solving separable differential equations. Generally speaking, if you have a multiplication sign, if you have dy dx equals a multiplication sign, then it's not hard to kind of multiply and divide all the x's to one side and all the y's to the other. But when you have plus signs, not so good. And so we're going to discover a brilliant idea that I don't know who came up with. Maybe that would be lost to antiquity. I was going to say I'd give it as an extra credit problem, but that could be a bottomless hole. Let's see, we seem to be struggling with sharing the screen here. Let's just retry. How to deal with the dreaded plus sign. So, okay, I know you see a black screen. No, you don't. Okay, good. Set time frozen, so I'm going to try resharing yet again. Seems like my computer is just like people, doesn't like to wake up early. Let's see, what are you seeing now? Oh, yeah. Do you see red writing?
Nope. See, your desktop?
Desktop, yeah, that's what I was afraid of. That's what I see too. Gosh, it's frustrating. Let's try resharing yet again. Finally. And then it goes black. Beautiful. Let's see. So let's just consider this differential equation. Dy dx equals, let's see, how do we want to do this? Let's make it a nice problem. X plus y with a plus sign.
It's I don't think it's showing still.
Yeah, we see your notepad, but we don't see what you're writing.
Okay. How about now?
Yeah.
There we go.
Do you agree that that plus sign is not good relative to what you now understand? I don't think I'll belabor this point a ton, but you might think, oh, I'll just subtract y to the other side. And I mentioned this quickly the other day, but it's like if you subtract y over there, the problem is, I'm going to erase this, but of course, if you have dy over dx and you have a minus y equals x, then what happens when you multiply by dx? Well, doesn't this get a dx as well, thanks to distributive law? And so you have not been able to separate them. The y and the dx are stuck together, and so this is not separable. So this falls into the category not of a separable differential equation, but ultimately what mathematicians call linear. And maybe because of the plus sign, you think, yeah, it looks kind of linear. But what are we going to do about this? And so we'll come back to that in a second. Not separable. So here's the genius of this. Now let me give you just kind of another problem that's kind of similar. If I told you this was your equation, x squared times dy dx plus 2x times y equals, we'll just leave something on the other side. I'll do something different. Let's put e to the x over there, something like that. Would you agree that looks much worse? But there's something really wonderful here. And this is kind of what we need to make happen. And what is wonderful here, my friends, is that I'm just going to write simpler example here so you don't think it has any connection to the previous problem. That is, this has no connection to the previous problem. If this simpler example was given to you, this would be really doable. Now the question is why? Well, do you see that this, what I have in brackets here, is actually the product rule? Let's think about this for a second. If I asked you to take the derivative of x squared times y, or better, I say find dy dx. Notice when you say take a derivative of something, it's really important, especially in this class, that you actually think, what are you taking the derivative with respect to? What letter? Because notice I have x's and y's. And so if we're going to take the derivative of x squared y with respect to x, and by the way, sometimes mathematicians would say, let's take the derivative of x squared y with respect to x. That might be how that was, how you were told to do that. That's the mathematical way to write that down, so you don't have to write out a bunch of words and so forth. Well, do you see the product rule there? Because you have x squared times y. So how does product rule work? Well, don't you take the derivative of one, leaving the other alone. Let's remind ourselves of the product rule. If I have a function, this is the way I always write it. If you have a function u times a function v, and those are both functions of x, that's like x times the sine of x, or tangent of x times e to the x, those two functions, and we're going to take the derivative. Don't you take the derivative of the first, leave the second alone, plus leave the first alone times the derivative of the second. Isn't that what the product rule says? That's what you do from Calc 1. Well, that's what I'm going to do here. In other words, don't I say, okay, well, I'll take the derivative of x squared. Notice, because we're taking the derivative of x squared with respect to x, that's really easy. That's 2x. But then we're going to leave the y alone. And then we're going to add to that the x squared left alone, but then times the derivative of y. Now remember, y is, in the language of differential equations, some equation. We don't know what it is yet. Y is some function of x. It could be something like sine of x times e to the x. So when you say, what's the derivative of y? You have to say, I don't know, because it's some function. I haven't figured out what it is yet. And so depending on how complicated it is, that's going to be a really ugly derivative. So what's the derivative of y with respect to x? It's the derivative of y with respect to x. In other words, I just have to say that I'm going to do it without doing it, which is exactly what I did up here. I said, I'm going to take the derivative of u. So I just wrote down the derivative of u. I don't know what it is. Do you see, my friends, that that happens to be exactly what is sitting up here? In other words, that is the product rule, if you will, having already been taken. somebody just finished taking the product rule. That's how that got expanded. And so it's, if you will, really wonderful that you have y here and then the derivative of y there. You have x squared here and then the derivative of x squared there. And so that is the product rule. It's like the product rule has just been taken. Well, if that's true, that just happens to be, and notice this very canned problem, like I totally set that up to be the case. Do you agree that if I just took that 2 away, that would screw the whole thing up? Or if I said, let's take that 2 away. Now it's totally screwed up, doesn't work. It's got to be exactly the product rule. So it's very canned. If that's true, then could we not kind of come down here and say, well, as complicated as that looks, let's see, if I work backwards, I'm writing down the non-derivative versions, right? The non-derivative versions. Well, let's see, I guess that'd be this and that'd be this. So it was like x squared y, and then I'm going to take the derivative of that. And that is still equal to e to the x. Now, this is a really beautiful idea, but it, you know, for me to say it once and so forth and have everybody go, okay, yeah, I get it, it's kind of unlikely. So please ask stupid questions, slow down. I mean, ask me to slow down, whatever, like, again, interrupt, as I always say, just interrupt. And can
you only make that assumption that x squared y prime equals e to the x? Can you only make that assumption because of the other formula that we got?
No, it has nothing to do with the original. Is that what you're asking, the red one?
Yeah.
No, this has nothing to do with it. I'm basically saying, let's say in the red that we wanted to try to solve this problem. And I'm saying that that's not separable.
I meant the green one.
Gotcha. Ask your question again. Maybe I didn't understand it.
X squared y prime equals e to the x. We can write that because of the green equation that it comes from, right?
Exactly. That's exactly right. So I replaced this chunk up here. I didn't do anything to the e to the x side. I just replaced all of that. I said, hey, that happens to be the product rule having just been taken. And so I went backwards and said, let's unproduct rule this. Usually the product rule, that's all you've ever done is kind of go forwards with the product rule. If you had something to take the derivative of quickly, I'm going to erase this. If I said, what's the derivative of x times the sine of x in previous classes? And so you said, oh yeah, I know what to do. I take the derivative of x, which is 1, times the sine of x left alone. And then I leave the x alone. And then I take the derivative of the cosine of x, right? Usually you go that way and you take the product rule and so you say, yeah, I found the derivative. That's really cool. What are we doing in this section? We're looking at this going, hey, that looks like the product rule has just been taken. And so we're going to go that direction.
Okay.
I want to answer your questions that occur, but also kind of just give you time to sort of process this. And so would you agree it's really hard to recognize? In other words, if I had just written this statement down right here and said, what do you notice about that? You all would have said nothing, right? You really got to be paying attention to think, hey, that looks like the product rule. Like you would not think that way, right? Like it's not obvious. And the same thing is true up here. This green expression, when you look at that, it would take somebody pointing it out for you to say, hey, somebody just took the product rule.
Hey, Doug, I'm with you on the undoing of the product rule, but I'm failing to catch up why we took the x squared y, why we're taking the derivative of x squared y and putting that equal to e to the x.
So all I did was I just replaced this. I took this here. I left this side alone. I said equals e to the x. I just copied that down there. And then I said, hey, this is the same thing as, well, this before you took the derivative. Do you agree with that?
We're going to proceed and then find a solution, but he's written it in a different form so that we can, there's more steps after this.
Yeah, like what good for you? Like, what does this do? I haven't answered that question yet. Like, what is that? What your question is, Kim? Why did you do that?
No, and this could very well just be that I have lots of cobwebs, lots of math cobwebs in my brain because I took Calc 4 last summer. But how did we get from, if you scroll up, how did we get from x squared times the derivative of y with respect to x plus 2xy is going to be the same as the derivative of x squared y?
Exactly. So take a look. Take a look right here. You just need time.
Okay.
If I say, let's go the forwards direction, the way you're used to be going. If I said, hey, let's take the expression x squared y and take its derivative with respect to x. And so that's what we did here. We said, okay, let's take that derivative. And we see the multiplication sign and we go, product rule, man, that's complicated. I got to think about this. And so to do that, we say, okay, well, you take the derivative of x squared, which is 2x with respect to x.
It just clicked. It just clicked.
Good.
I'm with you now.
Good. So we went, and that's exactly what I want you to do. Like, don't just sit there thinking everybody else gets this and I don't. Like, I want you to all have time to process.
Thank you.
Let's do one other kind of example. Would you agree this is also the product rule? If I said this is the, let's see.
Well, Doug, isn't the opposite of the derivative the integral? So wouldn't
Yep.
we just integrate?
That's
mean-
where we're going with this. That's exactly
Oh.
right. So the brilliance of this statement now is we can make progress with it. So we'll go do that in just 1 second. Would you agree this is also the product rule having been taken?
Is that equation in the red also with the equation in the blue above it?
Nothing to do with it. Brand new
Okay.
example.
Okay.
New canned example. Would you agree this statement right also right here is exactly the same as the previous one? Hey, someone just took the product rule. Can you unproduct rule that and tell me what it would be? The right side isn't changed, but what's another way to write the left side since the product rule has been taken?
The derivative of sine of x times y.
Sine of x times y, take the derivative of that. Do you agree with that? I didn't catch you said that. Again, do you see why I'm saying the word canned? Like, that's a miracle. It's amazing. The derivative of sine happens to be sitting right there as cosine.
It's still kind of hard for my brain to unravel it.
Now I'm going to show you a way to kind of not have to notice this so easily.
Right now, we've just rewritten it. So we're just saying that the first expression is equivalent to the second one. So that
Precisely.
we've just rewritten it in a form that's easier to deal with. It would be like, yeah, I was going to use an analogy, but I think it would make it more.
You can make it worse. I know what you're talking about. I do that a lot.
Well,
Well,
and
let's-
you're like undoing it.
So now, as one of you said, now that we're sitting here, now that somebody recognized that this ugly expression, which was linear, thanks to that kind of that plus sign, it wasn't separable thanks to there being a plus sign, then you proceed, you bypass all of that, write it like this, and now you integrate both sides. That's what's so cool about this. Well, does it make sense? Integrating just gets rid of the derivative. So now this side is just x squared y. And then over here, I just have to take the integral of that side. Do you agree with that?
So the left side wouldn't produce a constant, just for the technicalities, but the right side would, or would it still produce a constant?
I think it still does.
Okay, still does. Okay.
But then, as we've been saying, I could write plus C1 on the left, plus C2 on the right, and then just collect them on the left, or collect them on the right, whichever one. And so it's the integral of e to the x, fortunately, is just e to the x. Does it make sense I just solve for y? Because now all I have to do is divide by x squared. Bam, I did it.
So I'm just kind of confirming, I think with what Ben was saying, that when we undid the product rule, that created an X or a C, right? A constant.
Not when we undid the product rule, but when we integrated both sides. In other words, when I integrated both sides, and since the fundamental theorem of calculus says the opposite of a derivative is an integral, when I integrated this side to get rid of the derivative, then it just got my x squared y out from under the derivative, and I didn't have to take it. That's the beautiful thing. Because remember, I really don't want to take it, because if I do take it, I get, well, this nasty expression right here. And so the fact that I was able to do this basically meant I didn't have to mess with that left side.
Okay, I see.
Will we have to solve for C for a specific
Mhm.
equation in the slope field?
Yep. This will be like normal. In other words, you can just leave C in it, and then you can say, hey, look, I have a family of solutions, which is that slope field with all the answers. Or you might be given an initial value where you say, oh, at time 0, the answer is supposed to be 7, and then you'll get one of the members of the family, so to speak. So in this example right here, let's just finish this one really quick. If you wrote it this way, does it make sense? Now I could, again, integrate both sides. Now integrate both sides, and then that would just get rid of the derivative. Awesome. Again, technically there'd be a plus C over here. And then when I integrate x cubed, of course, that's not a hard integral to take. I get 1/4 x to the 4th plus another constant. And then I could subtract this over to the other side, and now I have kind of like a third constant. Again, this is a brand new example unrelated to the previous one. Just trying to get you to understand the concept. Do you see how easy it is to solve for y now, though? Because all I have to do is divide by, I never had to do anything to that left side. I just have to divide by the sine of x. Bam, solve for y. That was the goal the whole time, right? It's always to find this crazy function.
I think you just pulled a negative out of nowhere.
Yeah, I was
You're
gonna
correct.
say.
That definitely came from nowhere. You're right.
Yeah, I was like, wait a minute.
All I'm trying to get you to do right now is just kind of get the feel of the brilliance of this idea. But also, would you also agree that it's like, well, that's great, but how often is that ever going to happen? How often are you going to have a problem that you walk up to like this and like, oh, that's cool, that's the product rule? Do you agree that if this had been tangent, then it wouldn't have worked? Any other thing? E to the x? I mean, how many functions could I put right there? A billion. If you happen to put cosine of x there, it works. If you don't, it doesn't work. So doesn't this technique seem kind of pointless right now?
Why? Why wouldn't a tangent?
Because then it won't be product rule, because the derivative of sine isn't tangent. In other words, this expression right here has got to be the product rule, having just been taken. Otherwise, this doesn't work.
So Doug, if it was, let's say, cosine, and then if you put negative sign right there, that's still product rule, even though it shows a negative sign.
That's right. Mm-hmm.
That would immediately make me think it was like quotient rule or something. Like it would, the negative sign or the minus sign would throw me off.
Right. Yeah, I know exactly what you're saying. So what I'm saying basically is if you stare at a problem and, whatever happens to be sitting here miraculously, hey, there's its derivative right over there. Wow, wasn't that lucky? Then you're in business. But as I said, all I have to do is change that 2 to a 3. Doesn't work anymore. Change the x to an x squared. Go ahead, Kim.
Sorry. How does it still work if there's a change in sign?
It won't. Like if that was a negative, if this was a negative right here, it doesn't work because
It just works.
Not negative 2x.
It just worked in the case. It just worked in the case of the cosine times y. The derivative of that yields cosine times dy dx minus sine times y.
Yeah, because the derivative of cosine is negative sine, which means if this was cosine right here, then that would actually have to be negative sine So it's like, yeah, every single thing has got to line up. And so do you agree that this seems pointless? Like, well, great, but
Right. Connor was talking about a special case.
Got it. Okay, I misunderstood.
so back to our original problem then, is this going to work here? So let's copy this unit down below. And all of that was just playful to say, you know, is there something we could do with this expression? And now back to business. Meanwhile, our real problem here has been waiting. And so we say, okay, well, that's kind of cool. So then this would, is that a plus y? I remember that a minus y just to make it nice. Let's go back and make it a minus y just to make it nice. It doesn't matter. I just wanted it to be a nice problem. So then you might say, okay, well, that's not separable, but what we just saw a second ago is since there's a y and a y prime, remember this thing is just a y prime, that's another way to write it, right? So you have a y and a y prime, and so if I was to kind of move that over to the other side, so that it was, I just wanted it to be a plus sign over there. Does it make sense? That kind of has the look. That's kind of the look. That's what a linear, but is it working? Well, what's sitting right here? What's in front of the dy dx? There's not an equation there, but what's in front of it?
1.
1. So there's a 1 here. What has to be sitting right there in order for this to work?
Also a 1.
No,
0.
close. The derivative of 1, right? Whatever was sitting here, its derivative had to be sitting there, right? Whatever was sitting here, x squared, its derivative had to be sitting there, 2x. Is that true for us? No, because this would need to be a 0. The derivative of 1 is 0, so this doesn't work, but it does work. We just have to screw around a little bit. Let me show you something kind of brilliant. So this, as I said, it should be like, well, not helpful. But I'm going to do something sort of just from nowhere right now, but it's not going to be from nowhere ultimately. I'm going to do, like, this is just an equation, so I can do anything I want to both sides, right? So I'm going to do something rather surprising, and I'm going to multiply both sides by e to the x, so that now this thing becomes e to the x times dy dx plus e to the x times y equals e to the x times x. So that's okay, right? This algebra, there's nothing weird about that. The only thing weird is why did I multiply by e to the x? Number one, how did I know to do that? Number two, why did I pick e to the x? Why not multiply both sides by tangent or natural log or something like that? But what just happened?
You have the derivative now of e to the x on y.
Now the right side got more complicated, but would you agree that the expression right here, its derivative now is sitting right here, and e to the x, of course, is a really unusual case because it's its derivative. But does it make sense I could now proceed thanks to this, you know, rather brilliant idea?
Is that going to be like a universal tool? Is just multiply everything by e to the x?
I was going to say that's what I'm going to do for every linear equation now.
Yeah.
Well, the key is that the universal tool is to multiply every one of these by something, but it just won't always be e to the x. I'm going to show you how to figure out what that thing is in a little bit. In this case, it just happened to be e to the x, but I'm going to show you how not to have to guess. You're never going to have to stare at it and go, let's see, I think I'll multiply both sides by x times the tangent of x. And oh my God, it worked, you know, after 19 tries or whatever. You're not going to have to guess. But let's first proceed with this and show that it actually works. So my question is, could you now rewrite, like, you know that the right side has not changed, but can you now rewrite this left side as the derivative of junk? Do you understand that you're writing the non-derivatives? Do you understand that, and this is a little harder to see, but this was a derivative having been taken, and that's also a derivative. And so if you're kind of working backwards, it's really this and this that were sitting there kind of before the derivative was taken. Does that make sense? in the product rule. So now, as before, I'm going to integrate both sides. When I do so, that just gets rid of the derivative, fundamental theorem of calculus, which is very exciting because remember, that's what you always have to do with a differential equation, meaning an equation with the derivative in it is to underivative. You got to integrate it to get rid of the derivative. Well, we just did that. And then fortunately, that left side was really simple. Now, is the right side really simple?
There's going to be parts.
Nice, good memory. Calc 2, when there's junk times junk, that's integration by parts. Let's see. I think I'm gonna quickly build this from scratch. For most of you, that was like a couple of terms ago, and for some of you, it was even a year plus a couple of terms ago. And so you don't just have that in the front of your mind. Again, a calculus book is going to assume, yeah, it was just like it was yesterday, and you're still really good at it, which is one of the things that makes all math classes feel hard because it's assumed that you're awesome at whatever the previous math class was, right? But let's just build this for ourselves again. I don't have integration by parts memorized. What is it? Well, you write out the product rule. And again, I don't know if this is the way you learned it, but this is just such an easy way to remember it. That's the product rule, right? And remember, u is really some function of x. Could be sine of x, e to the x, and v is also some function of x. I don't even know what it is. And so those aren't just letters. They're any function of x I want to stick in there. And now if you come back and say, I am going to integrate both sides, then on the left side, that just gets rid of your derivative. On the right side, well, nothing happens at all. I'm just going to write it down. And so if I just subtract this over to the other side, subtract one of them to the other side, that is integration by parts. Except I think I subtracted the wrong one to the other side. I did. I'll subtract this one to the other side. No, I didn't.
No, I think you did it right the first time.
I did. I did it right the first time.
Because it's VDU, or I don't know.
Yeah. So the idea with integration by parts is if you're sitting here staring at an integral and you're like, man, that's hard, and that's what I'm doing right now. I'm looking at like junk times junk and I'm going, man, that's hard. And I know that like product rules, the forwards version, the derivative version. So it's like, this is like unproduct rule. It's like, oh, my head explodes. So you're sitting here staring at this thing and you think, well, I don't really know how to do that. Well, could you do this instead? Instead of one times another, could you kind of switch it up a little bit? So what does that mean? Again, this should ring a bell to you, but so if I let this one be the u and this one be the v prime, then if I'm sitting here trying to take the integral of x e to the x and I say I can't do it, well, then I could take the integral instead of what this side said, which is u times v. And notice since u is x, then that means u prime would be 1. Since v prime is e to the x, then that means v would also be e to the x, since derivatives and integrals of e to the x are so simple. So u times v would be x times e to the x. And you might think, oh, that's not any better. But notice there's no integral sign in front of it. I don't care how ugly that is. I don't have to do anything to it. Minus, I still have to take an integral, but of what? Well, something different. U prime v. U prime, though, is 1, and v is e to the x. And so notice I just got rid of the fact there's no more product rule anymore. So, this made an integral that was easier for me to take. So I did it. And of course, the integral of e to the x is e to the x. And so there, I did it. So now I'm just rewriting, I'm sort of going from here down to here. I'm saying e to the xy is equal to x e to the x minus e to the x. I didn't have to take the integral of the left side. I did take the integral of the right. I got an ugly answer. Remember, when you take an integral, there's really a plus c for a constant. And notice now how easy it is to solve for y. So y is equal to, I'll go ahead and write all of this out. And you might say, that doesn't look very simple. So I think I will simplify it. X distributive law, x e to the x divided by e to the x would just be x. E to the x divided by e to the x would just be 1. And then what would I do with c over e to the x? Would you agree it's easier to write it as c e to the negative x? Would you agree that's a nicer answer?
It's definitely more streamlined.
Yeah, it's kind of a little bit more streamlined, but remember, you know, there was a time when I was sitting here staring at this question, thinking, how do I solve it? And I now think I just did. Now, there was a lot of miracles that happened, right? Like one miracle was this crazy idea of recognizing a derivative, recognizing the product rule. But even to make that happen, there was the miracle that I just kind of invented from nowhere to multiply both sides by e to the x, right? So you should say, well, yeah, I think that actually is the answer, but you know, I'm not going to be able to repeat this for any other type of problem, right? But let's just quickly play with this a second. Let's kind of just convince ourselves that that really is the answer. So notice there's the slope field. Here's the family of solutions. Notice again, that kind of has like a parabola that's been laid over on its side, sort of.
We're just seeing a
You can see
desktop.
desktop now, yeah.
You're just seeing a desktop. Dang it, why not? I just said share screen. What do you see now? Still same thing? Aren't you seeing
Desktop
GeoGebra?
now. We saw it before, but let's see. There, now you see GeoGebra, right?
Yep, there we go.
So dy dx, remember that's a very confusing way to say that. It says f prime of xy, but it's dy dx. The slope is a function of x and y, and over here, sure enough, there's an x and a y. And that was our equation, x minus y. And again, you look at this and you say, okay, well, yeah, those look the same. But then if I go over here, notice they don't look the same. So again, what's kind of cool about this is no matter where you start, it's sort of exiting the stage over here in the upper right-hand corner. But again, what we're getting is a family of solutions there, and this green represents all the different answers for different C values we can get. And again, most of us would not look at this and say, hey, isn't that, you know, x, isn't that like x plus 1 with an e to the x term? Like that's what we said the answer was, right? That doesn't really make a whole lot of sense. Let's go to Desmos. Didn't we just get done saying that the solution to this was y equals x minus 1, which of course is a line. But then what happens if I add a c times e raised, that's not an e, raised to the negative x power? That's what we're saying the solution is, correct? Look at that. Isn't that indeed what we just saw? Again, I'm just showing you this because I'm giving you time to think, but also you should be doing this with every problem. You don't need me to tell you you're right. I'm giving you even problems in the back of the book. And so you can't just look in the back and go, oh, look, I got it right. You got to check it yourself. Again, you don't recognize this as the red graph. It's not like you look at that and go, isn't that a line added to an exponential function? Like, I think I recognize that. Like, we don't recognize that, right? It's too weird. But the point is it's working. Like, we're not good at it, and you're not good at it yet, but it's actually working. We just solved a non-separable differential equation using a ridiculously brilliant trick. You know, who thinks of these things? Questions, comments? How's your brain doing?
If you put, could you slide, oh darn, it went away. If you
I
slid
can bring
the
it right back.
C, if you slid the C to 0, would it just be a line?
Yeah, think about 0. If you slid C to 0, you'd have x minus 1 plus 0. Then that's exactly the case where there is no exponential term, and then you just have the line. And so again, that'd be the equivalent of saying, hey, my pool, I really would like my pool to be at a 6.8 pH. And then you say, okay, well, what is it right now? And the answer is, well, it's at 6.8 right now. Well, then you're on, you're done, you're there. Does that make sense? Any other place, you're gonna have to work your way up to the right pH or work your way down to the right pH. But in this case, your initial condition was, oh, you're already there. So again, we're stopping here and just saying we're going to let the answer be a family of solutions. We're going to just let it be all of them and not worry about going and finding the constant. But the larger, more practical version of this is where you say, okay, great, now I've done this. And so then let's list an initial condition. Let's say that y of 0 is supposed to be 7 or something like that. And then we can actually go get one of the particular solutions. And of course, if that's your pool, that would be the only one you cared about, right? And so that's the idea. In the real world, you would never stop at a family of solutions. Only a mathematician would stop there.
But in the real world, it's really important we get that y equals 7 value. And then we could just make everything else happen.
Mm-hmm. That's right.
All right.
And remember with Euler's method, before we knew how to even solve these ourselves, we said, if you knew that you wanted to start at 0, 7, you could actually just use the slope formula x minus y and actually create a graph that creeped along it. And you'd have a graph which would actually allow you to answer all your practical questions without ever even knowing what the original equation is. That's kind of the thing I think that's fascinating about this. And since we'd be solving this numerically, not mathematically. So there's a lot to get your mind around here. So I just gave you time to think, really, but I sort of convinced you that this was actually correct. It worked, as crazy as this was. Go ahead, Ben.
Oh, I was puzzled by one thing, though, because when we take the derivative of that equation right there, we don't get x minus y.
Oh, there's a wonderful question. Ben just said, and isn't that another way to check your work? If we take the derivative of this, should we not get x minus y according to the original up here? And so based on the graph I just showed, it seems like that should have worked, right? But that's worth checking too. Let's go do it. So if I find dy dx, the derivative of x is 1, the derivative of 1 is 0, the derivative of c e to the negative x is negative c e to the negative x. Is this true?
Yes.
So you get dy dx equals 1 minus c e to the negative x. And so is Ben correct? We did not get the right answer.
I'm sure there's some manipulation you could do with that.
Think about what this says right up here. What's another way to write c e to the negative x?
Oh, okay, I see it now. That's cool.
Isn't that kind of cool?
That's cool.
Yeah.
So I love that you pointed that out. If I'd have thought of that, I would have pointed it out myself. So that was really cool. So this answer we just got is not wrong, but c e to the negative x is actually apparently equal to y minus x plus 1, isn't it? So c e to the negative x could also be thought of as being equal to y, subtract x over, add 1 over. So then if I replaced this right here, when you have 1 minus 1, which is gone, and then you have negative 1 minus, you have 1 minus all of that stuff. So it'd be a minus y would turn into a plus x, and that'd be a minus 1. Sure enough, isn't that x minus y? So it did work, but we did have to mess with it a little bit to check that. So that's another awesome way to check your work. So that really is the right answer. Awesome. Now, all we got to do now is think about how did I know in this case, because it'll never, this is a, this is just one random example. Like, how did I know to multiply both sides by e to the x? And so I want to show you now how to figure out what to multiply both sides by so that it will end up as the product rule sitting there every time and you won't even have to think about it. Huh? Okay, well, let's go down and answer the huh. So pattern, let's find a pattern for this that we can now use to solve all problems of this crazy type. And again, I want you to notice we're learning a technique to solve one type of differential equation. It's the linear type. We have one method separable, and that's the best one. It's super easy relative to other methods. And so, anytime I can see that it's separable, do it that way. But if it isn't separable, maybe it's linear. If it's linear, this technique will work. And so let's consider the equation dy dx plus, I think I'll call it p, y equals some other function on the other side. In other words, this is some function of x. This is some function of x. How come I didn't put anything right here? Couldn't there be some function of x in front of that too?
You want it written in standard form?
Does it make sense? There doesn't have to ever be anything in front of that. So let me just give you a quick example just to make sure you get the feel of this, because you're gonna have to do this a lot. Let's say you were sitting here with like x times dy dx plus x to the fifth y equals sine of x or something like that. Could you get rid of that if you wanted to right there? What would you have to do if you said, I don't want that there?
You'd have to pull an x out.
Can't you just divide both sides by x to get rid of it? Like, just like I multiply both sides by e to the x, couldn't you divide by whatever that is? So now this becomes dy dx equals, well, in this case, we got lucky, x to the fifth over x actually simplifies. And so not equals, it's plus sign. X to the fourth y equals, and notice over here, I don't get lucky. I just have to write it that way. So do you agree you never have to have anything in front of the dy dx if you don't want it? Even if the problem had something in front of it, and it did for us, right? Every problem well, that's not true. The last one we didn't. But you never have to have anything in front of it. So the point is this, so your p of x function is x to the fourth. And this is your q of x function over here. And so the point is you're gonna have probably some function in front of the y and some function on the other side, but you never have to have anything in front of the dy dx, right? Now, it is at this point a minute ago that I said, hey, let's multiply both sides by e to the x, right? And then suddenly the product rule was sitting there and everything was wonderful, right? So let's multiply both sides, but let's not just say it's e to the x every time. Let's multiply both sides by some function we're going to invent. And I'm using your book symbols for this. This is the Greek symbol, mu, mu. Mu, let's multiply both sides by mu, some new function. It won't always be e to the x. So that mu times dy dx. Are you okay if I don't say the as a function of x part? The point is it's some function of x. And when I do that, then the p will get also multiplied, whatever that function is, will also get multiplied by it. And then whatever's on the other side will also get multiplied by it.
Are we gonna get a list of like cool mu equations to use?
Even better, we're going to come up with a formula here that's going to tell us how to find it.
Okay.
So it won't even be a list, which that's a wonderful question. So, Raymond's point is like, are we going to get some way to figure out what that is? Like, this is no good if that doesn't help. And so does it make sense?
So mu times p has to be equal to the derivative of mu?
If that's going to be the product rule, Say what you just said again, David. I think it was David.
So mu times p has to be equal to the derivative of mu in order for it to satisfy the product rule.
Is he right?
Yes.
In order for this to work, in order for this to be the product rule, then is it not true? Hence, I love the word hence. Then if I take the derivative of the mu function, then it darn well better be equal to what's sitting over there, right? Isn't that what we always said? Whatever's sitting right here, its derivative needs to be sitting right there. Isn't that what we've been saying? Again, would you agree with me? It's like, yeah, not helpful. This is not helping.
Well, now you have another differential equation to solve.
But the point is, this is a solvable differential equation. And remember, these are, I'm just reminding us because I don't think this is obvious. This is really easy to get kind of lost. These are functions of x. Mu is some function of x, p is some function of x. So that means mu prime could be thought of as, d mu dx, right? It's a function of x that's equal to mu times p. Well, notice this is actually solvable. This is a solvable, unfortunately, it's a solvable separable differential equation. This is actually separable. I can actually solve this. In other words, I can figure out what mu is. We have, as David said, a brand new differential equation here. And if I can solve this, then I'll actually know what mu is. Every time, not mu just for a certain problem, but for all problems. I have a solvable, separable, ordinary differential equation here. Okay, well, let's do that. Remember, we need to get all the mu's on the same side, you should say. So that's easy. I'll just take d mu and divide both sides by mu. Look, there's notice there's no plus signs over there. I like that. So I can get that on the other side, and then I can multiply dx over to this side. And now I can take the integral of both sides like we did in the previous section. What's the integral of 1 over mu with respect to mu?
ln mu.
Natural log of mu. Again, plus c. What's the integral of p with respect to dx? Notice you can't answer that because you don't know what function that is. Remember, p could be sine of x. Oh yeah, that's one answer. It could be e to the x. That's another answer. Could be tangent cubed. So it's like I can't take that integral because I don't know what p is. It's a function of x and I don't know what it is. So I can't take its integral, right? Until I know what it is, I can't take its integral. Now remember, when we get back to these problems, aren't you going to know what it is? Like if you're given a problem, isn't that actually a function right there? That's going to be something you can stare at, right? It's not like this isn't going to be known. We're going to know what that is. We're going to be able to stare at it and go, hey, it's x squared, right? Look right here. Well, it's x to the fourth. Yeah, I know what that is. We're going to know what it is. We just don't know right now. So I can't really do anything over here. So one more step. How do you solve for mu?
Mu is everything to e to the x, or e.
Yeah, mu equals e raised to the integral of that function. Now, where's all the plus c's here? How come I don't have any plus c's?
We're gonna differentiate later anyway.
I
Just
can
like
pick
for the
anything
end.
I want. That's not an obvious answer. I can pick anything I want for that. So I'm going to pick 0 because it can be any c, right? Well, I just want it to be 0. I don't want any c's. I want it to be nothing. There's how you find mu right there. You don't have to guess.
So then would we go back and replace p with x to the fourth?
Exactly. So earlier I multiplied both sides by e to the x. How did I know to do that?
Because it was you had a 1 in front of it.
Yeah,
Or
let's
the
think about,
function 1. And
Yeah,
so
let's
then
think about
integrated
that.
with X.
Right here, what was that value? It was a 1. So then we say, okay, well then mu is found by taking e to the integral of 1 with respect to x. Well, isn't that e to the x? The integral of 1 is x, so it's e to the x. Mu is e to the x, that's the multiplier. So that's how I knew to pick e to the x. Let's see, now I just made this other problem up with x to the 4th in it down here. I don't know if this could be a terrible idea. Let me stare at it. Remember, multiplying both sides by e to the x, though, creates havoc on the other side. When I did that, this side over here got ugly, right? And I actually had to take that integral on that side. So it is possible to, create problems where the integral that you have to take on the other side is really ridiculous. And so maybe the one that I made up a second ago with x to the 4th isn't a great example. But let's go ahead and at least pursue it anyway.
By parts a couple of times.
So yeah, let's just kind of reconsider this one for a second. I think it is going to be ugly, but let's just go ahead and do it. Let's at least start it. So there's our P. So then we say, okay, well, this isn't hard. Mu can be found by taking e, not the integral of e. The integral is always e to the something. Now, I would like you to stop and think, why is that a brilliant idea? You're always going to multiply both sides by e to the something. It just isn't always going to be e to the x. Well, that's because the integral of e to the junk is e to the junk. Can you see how that would help this work?
Right, chain rule.
Yeah, because it's kind of chain rule-ish. So I need to take the integral of x to the 4th with respect to x. Well, fortunately, that's not a terrible integral to take. So x to the 4th is 1/5 x cubed. I'm sorry, 1/5 x to the 5th. So I'd have to multiply both sides by e to the 1/5 x to the 5th power. That's my multiplier. That's what mu is, multiplier. And by the way, that's probably why they picked mu, m for multiplier. Or perhaps this was invented in a different language where the word multiplier didn't start with an m, and I have no idea what I'm talking about. I'd say that's more likely, by the way. But that worked good for us. Okay, so now I'm going to multiply both sides by that. So you're saying if I multiply both sides by e to the 1/5 x to the 5th, that's what would happen to the first term. What happens to this next term? I get x to the 4th is already sitting there, but now I'm going to multiply it by e to the 1/5 x to the 5th. And there's a y already sitting there. Yeah, this problem's going to be terrible. And on the other side, there was a sine of x over x, and it's going to be multiplied by 1/5 e to the x. What am I talking about? E to the, I don't know what I'm talking about. It's going to be multiplied by e to the 1/5 x to the 5th. Now, this looks horrible, but the question is, did it work? Is this the product rule?
Yes.
It is, because what's the derivative of e to the junk? It's e to the junk times the derivative of the junk, but isn't the derivative of 1/5 x to the 5th, x to the 4th? Can you see that this derivative is actually sitting there? I mean, that actually worked, which means as ugly as the right-hand side is, how can I rewrite the left side? Remember, it's the non-derivative terms that you're writing down.
E to the 1/5 x to the 5th times y.
Correct. The non-derivative terms. So it's working. I mean, isn't that crazy? Like, you never would have stared at this and said, oh, I see what I need to do. I just need to multiply both sides by e to the 1/5 x to the 5th, and then it'll be the product rule. You never would have been able to just see that. Now, why is this still a terrible problem?
Because integrating the right side would suck.
Yeah, the right side.
I wish I could say that any clearer. So I'll just
I don't
repeat it.
think I don't think I know how to do that.
I don't think I do either. Notice it's 3 different functions. So it's like the product rule. And so but I actually like this happened because again, one of the problems with textbooks is they make it just look like everything works out great. But remember, somebody is very carefully handing you questions that will work based on how much you know about math. But there's lots of problems that aren't solvable. So if I now proceed to take the integrand, take the integrand of both sides or integrate both sides, the left side is the whole point of all of this. Like that worked really awesome because notice the y is now there and all I have to do to solve the left side for y is divide by 1/5 x to the 5th. What am I doing? I keep writing that down wrong. I could have just stuck an e down there and not redone this, couldn't I? But then I got to take the integral of the right side and that's not happening. So this is not a good question.
That's what the internet is for.
The book has to make up the right side because you're always going to be multiplying by something. So the right side is going to get ugly naturally. And in my case, it got really ugly. So if assuming I could succeed with the right side, then all I'd have to do is divide by e to the 1/5 x to the 5th, and I would have solved for y. Does that make sense? But that's just good at least to see. Okay, well, let's just pick some book problems down, see if we can actually survive some questions. Let's see. Now, why am I picking book problems instead of making them up? Well, I just illustrated why, because you got to be really careful to make these up in such a way that the integral on the right side isn't too complicated. Otherwise, you're in terrible shape. Let's see. I'm looking at question 2. Looking at question 2 in your assignment. I'm assuming because it's question 2, it won't be terrible. 2.3, question 2. And they say the problem is x squared dy dx plus the sine of x minus y equals 0. So it has a linear look. Like, what do we not like about this problem? We don't like the plus and minus signs. Plus and minus signs mean it's not going to be separable. Separable is multiplication and division signs. I see a bunch of plus signs. Well, that's why it's called linear. Isn't that what linear equations look like? They have plus signs like 2x plus 3, not 2x times 3. So for a person to look at this and go, not separable, can't use that method. That's linear. I wonder if this little mu technique will work. Well, what you should think is I need the dy dx and the y terms on one side and the non-y terms on the other side. That's like should be your logic. So you're thinking for this. And so you should say, okay, cool. X squared dy dx. I like there's the derivative. And then there's the y term, but I really don't want that sine of x on this side. It's that function that's on the other side, right? It's that I don't really care what's on that side. And so does it start to look like a little more like we've been trying to get these to look? What's my next move here?
Multiply everything by mu.
Yes, except to find mu, what has to happen to this guy here? How did we find mu a second ago? What condition was this problem in? This original red equation, what condition was that in when we went mu hunting?
It was not in front of the derivative for dy.
There was nothing in front of this, right? So before we go mu hunting, we've got to get rid of that x squared. So our next move is actually to divide by x squared. Would you agree the right side is looking a little terrifying?
Yes.
But does it make sense? Now I can say for the first time, I know what this p function is. There it is. If I don't do that, then I look at the number in front of y and I think that's p. P is -1. Well, it's not -1. It's actually -1 over x squared. Like it has to be in this form to go mu hunting. So mu is found, the multiplier is found by taking e And raising it to, well, I got to find the integral of that. Well, that's negative. I'm going to write it as x to the negative 2 power. I got to take the integral of negative x to the negative 2 power. Fortunately, that's not terrible. That's just power rule. What do? I add 1 to that. Negative 2 becomes positive. I'm sorry, becomes, because you're adding 1 to it. It becomes negative 1. So it's negative x to the negative 1. But then you divide by negative 1, right? So it actually becomes just e to the positive. Let's see. Yeah, e to the positive x. But it's to the negative 1 power. There's my multiplier. Now, again, I find myself going, I hope this is working because I'm not seeing it. Do you agree with that? I don't think I screwed up the integral, but I'm not seeing this working. So what you're saying is if I multiply both sides by e to the x to the negative 1 power, and I'm really looking at the right side as being suspect now, because it's like, aren't I going to have to take the integral of that side? That just makes no sense to me. How am I going to be able to do that? And I'm truly thinking that right now.
It's not going well for me with.
It's not going well. And so now for the first time, I go over and look at the directions. Anybody read the directions to question the first 6 questions that I didn't read?
Oh,
What is it?
It says, determine whether the given equation is separable, linear, or linear. It doesn't say to solve it.
oh, that's great.
We'll go ahead and proceed, but we're not, this is going to be just like the previous problem. Like, no wonder they didn't say to solve it, because I was thinking, but let's just check to see, did this actually work? Be really helpful if I read the directions. I'm glad my dad's not here right now. He always tells me that. Did that actually work? Did the mu thing work? Is that the product rule sitting over there? Because I find myself going, I don't know.
Take the derivative and find out.
Let's take the derivative of e to the x to the negative 1 power. Well, the derivative of e to the junk is e to the junk, right? But what's chain rule say? Times the derivative of the junk. What's the derivative of x to the negative 1? Well, don't you
X to the negative 2.
don't you multiply the exponent down front, right? And then subtract 1 from the exponent? Isn't that true? Is that how you take a derivative, right? So if it had a little easier example, if it had been something like ex to the 7th, wouldn't you say the derivative is ex to the 7th, the derivative of e to the junk is e to the junk, times the derivative of x to the 7th, which is that? You bring the 7 down front, subtract 1. Wasn't that what I just did? I brought the negative 1 down front and subtracted 1 from negative 1. Didn't do anything different, right? Did it work? Did the mu trick work? Sure enough. Isn't that exactly what's sitting right here? Exactly. Isn't that exactly what we just got?
Looks like it.
So sure enough, so then I'd be able to say, okay, well, I have ex to the negative 1 times y. Again, it's kind of like this term and this term. And if I unproduct rule it, that would be the product rule having before it had been taken. And then the other side is this ugly business. And then I could integrate both sides and I'd have ex to the negative 1 y equals the integral of ugly. And if I could survive the integral of ugly, I'd divide by ex to the negative 1 and I'd be done, right? Now I look and it says in problem 7 through 16, obtain the general solution, actually solve these problems. And so let's go try to solve, well, how about number 9? Number 9 looks like we'll actually be able to solve that. We need to practice on what we just did anyway.
What is
so.
one that we could not solve?
This one. This one right here.
I think he means one where the integrating factor wouldn't work.
Yeah,
Oh.
one where just you get to the end and it's the integrating part that doesn't work.
Well, the reason they asked the first question about things being linear and so forth, like if this original problem right here had been a y squared, then this wouldn't work.
Mm-hmm.
This whole trick wouldn't even work. And that's why the first one, chapter 1.1 was asking questions like, what's the definition of a linear function? And, I talked about it, but didn't go into it in great detail. That squared would be a deal breaker. If this thing was squared, that'd be a deal breaker. Linear means no squared terms, right? If I say y equals 2x plus 3 is not a line, but if I say y equals 2x squared plus 3, is it a line? No, it's not squared. It's squared now. Well, notice it's just dy dx, not dy dx squared. It's just y, not y squared. And so linear is a very tight definition. So again, you don't notice that when you do the problems because they're, of course, going to give you problems you can actually solve. They're not going to say solve this, and then you can't do it with the techniques you have. Not sure if I answered your question. So let's look at question 9. I'm going to let you get a tiny head start on this. Very tiny. When you get this in the right form, try to get it in the right form and get mu figured out. Like, what's mu? What am I multiplying both sides by? Set this process up.
Kind of like the example you used before.
Yeah, so my first move, you should say, I can't have that x in front. It's got to be empty. So I will divide everything by x. And instead of writing 2 over x, I'm going to write it as 2x to the negative 1. Now notice something wonderful happens on the right side. What happens on the right side this time?
This can actually combine, so.
You can combine those. So that's what we don't want. Like, we don't want to have is what happened in the last problem, which is you can't combine them. There's like all different functions. There's a trig and there's an exponential and there's a parabola, and you can't put them together. And so that's going to be a terrible integral. Well, this isn't going to be so terrible this time because I can actually put those together. So this would be x to the positive 1. If I moved it to the top, that'd be x to the negative 4. So it's like, oh, there was a negative 3. Now there's a negative 4. So what? It's not that much different. So then we go mu hunting. Multipliers can be found by taking e and raise it to the integral of whatever that p term is right here. Now that's maybe why you can see why I wrote it. Instead of writing it as 2 over x. Actually, now that I think about it, all of a sudden I'm thinking that was a bad idea. But let's just go ahead and leave it alone. What do you do to find the integral? You add 1 to that x. So it becomes x to the 0, and then you divide by 0. Notice that didn't work.
It's got to be ln or natural log. You got to.
Yeah. This is the one case that didn't work. And so as it turns out, it might have been sort of better if I had not written it that way. I thought I was going to make our life easier by doing that. Maybe if I had written it this way, you would have kind of noticed that. So then you say, oh, the integral of 2 over x is just 2 natural log of x. Now that's also a pretty ugly multiplier unless you actually know how to clean that mess up. How's your algebra skills? That does not have to look as ugly as it looks right now. Do you understand that? If you multiplied both sides by that, you'd make this problem pretty hard. But do you understand that that is the same as e to the natural log of x squared? Can't that 2 go up and be the exponent of what you're taking the natural log of? And then what's e to the natural log of junk? E and natural log cancel each other out. In other words, your mu is actually just x squared. If you notice that, your life will be easier. If you don't notice that, it won't be easier. So notice, oddly, in this case, it isn't always an E. Like you're not multiplying both sides by E to the something. It actually, the E went away here, which is sort of weird, isn't it? Now, again, I find myself going, really? Like, is that really the multiplier? Well, let's go see. So if I multiplied x squared, and I'm going back to, you know, this portion of the equation, then I'd multiply this by x squared. And when I multiply 2 over x by x squared, oh my gosh, look at that. That is awesome. I can't believe that just happened. Isn't that amazing? Sure enough, totally worked, didn't it? Look what's sitting there, x squared and 2x. Oh, wow, that's cool. Totally worked. Never would have noticed that. Amazing. So I'm really thankful for what mathematicians do. We're, you know, trying to come up with a formula, a pattern, a way to find the multiplier so that we don't have to stare at it and, you know, look at a chart like Raymond was wondering if it was going to happen, or, you know, something of that nature. Like I have a way I can just go find it. I mean, that's, and every time I do this and I write it all out and it's like, oh my God, that actually worked. I just find myself going, that's amazing. I can't believe that worked. That's just so cool.
But it's always going to involve manipulating E, right?
Correct. That's right. And again, your intuition on that should kind of make sense. In other words, if what is sitting here, its derivative needs to sit here, but I have to, when I multiply, I have to multiply it by both of these. I can't just do it to one. It sort of makes sense it would have an e to the x in it because e to the x is its own derivative. And so if I multiplied it by both of them, it would work. That's the only thing it would work. So of course, this right-hand side, again, notice that isn't even two things. This just turns into x to the negative 2. So notice now when I take the integral of the left side, I'm like, oh, whew, that's going to be easy. I don't even have to do integration by parts. There's not even 2 terms over there, let alone 3. And so, oh, that right side's not going to be a terrible integral. So I say, okay, well, what is the product rule before it was taken? It's this term and this term. Those are the non-derivative terms. 2x was a derivative term. dy dx was the derivative term. So it's x squared y, its derivative is equal to x to the negative 2. And now I can take the integral, not the derivative, the integral of both sides. Or integrate. What is that? Action word, verb. Integrate is the verb. So if I integrate, that just gets rid of the derivative on the left side, and integrating x to the negative 2 is a super easy integral to take because I add 1 to it, becomes negative 1, then I divide by negative 1. And there is a plus c. There's, again, technically 2 plus c's. But notice I'm, well, done. This is really easy. I just have to divide by x squared. Notice how important the c is, because the c is, in a sense, no longer just a constant. It's now the coefficient in front of x to the negative 2. In other words, what happens to this mess? Oops, I wrote negative x. I'm sorry. You're always staring at what I'm writing that's incorrect and getting lost because you're paying attention to that. So wouldn't that be negative x to the negative 3? Or I'm going to go ahead and write it like this. I just think it looks cooler. I don't like negative exponents. I get confused when I stare at them. So the c is actually the coefficient in front of 1 over x squared, or in front of x to the negative 2. Now this problem, in the way it worded it, it said to obtain the general solution to the equation. What does that mean, general solution?
The one that hasn't been given an initial condition yet.
Yeah, you haven't been given an initial condition, so you're getting the family of solutions. You're getting the entire slope field. You're getting all the answers. So they're saying, you know, let's make the problem stop as soon as possible. Good for them. So I think this is my answer. Now, let's take, I don't know, Ben's idea earlier. Like if can I check and see if, like, is that really the solution to this? Does that really work? Y, if I plug y back into this, notice if I plug y back into this, I would just plug it in right there. Because to check and see if I'm sort of questioning, are these equal, I plug y in there, great, no problem. But notice here, I've actually got to plug the derivative of y in there. And if I do that, notice I'll have no more y's and I'll just have x's, and then I can just kind of proceed to see, are those both sides actually equal? For any c, no matter what that constant is. So I'm checking my work. I'm saying question mark. Is that really true? Did I screw up here somewhere? Either because I have no idea what I'm doing or because I just did something stupid, like wrote something down wrong. Or simplified the exponents wrong, like I screwed the exponent rules up or something like that. I mean, there's just so many things I could do wrong here that it's unfathomable. Now that I see I have to take the derivative of this, I'm sort of more inclined to think even though I don't like to see it this way, I'd rather kind of write it like that. Would you agree that's an easier derivative to take? Because in the blue form, it's kind of like quotient rule. So although I don't like negative exponents, that's an easier way to take it. So there's what y is equal to. So I can throw that in for y. But then let's go find out what dy dx is equal to. Well, that's an easy derivative. Take -3, multiply it down front, becomes +3, and then subtract 1 from that. Make sure you don't get -2. That'd be an easy dumb mistake to make. Also, we're doing integrals and derivatives back and forth all the time, so it's kind of easy to like mix up, or am I taking a derivative or an integral? But a derivative is multiply the coefficient or the exponent down front and then subtract 1 from it. Multiply the coefficient down front and then subtract 1 from it. So I'm now prepared to plug all that junk in here and here, prepared to plug that in. So the original problem said x times dy dx, which I think is this. It's supposed to be 3 plus 2 times just y without a derivative, which is this. And supposedly that's just going to equal x to -3. And I find myself going, no way. That just seems too complicated, and there's no way I didn't make any dumb mistakes in all of the thinking I just did. I made no dumb mistakes anywhere. If that happens, I'm just going to be surprised. It's going to be an utter miracle. So let's see, what do I get? I distribute x in here, so that gives me 3x to the -3, does it not? X to the first times x to the -4th, you add exponents. Minus 2c, x to the first times x to the -3rd is x to the -2nd, plus 2 multiplied by everything. But that was actually a negative, so I'll switch it out front. -2x to the -3, and then negative plus 2 times c. And again, I'm sitting here wondering, is that equal to x to the -3? Forgot the c right there. And then I notice, look at this. That is exactly the same as that, except for one is a plus 2c, one is a minus 2c. And then I look at what's left and I go, oh my gosh, those are like terms. 3 of them minus 2 of them is 1 of them. This is actually 1x to the -3. Oh my gosh, ching, it really is equal. All right, it's a miracle. In my case, I usually get these right because you guys all interrupt me and tell me what dumb mistakes I make. But in your case, or when I'm alone, I usually have to go back and find out, what thing I did wrong. Isn't this amazing? I mean, isn't this a crazy idea that somebody came up with?
This is really good stuff.
I mean, isn't it? This is beautiful. I mean, I hope you have terrifying. I mean, it's like you want to pass this class. I mean, you're really in here because you have a job you want to get someday, right? I mean, that's why you're really in this class. Maybe ultimately, but this is still beautiful, and not many people ever get to see this. This is, as I often say in my math classes, this is a beautiful waterfall, but it's a 20-mile hike. Like not everybody can survive that. Like we're way out here right now, but it's like, this is amazing. And what amazes me, and I say this a lot too, is like somebody had to think this up. I'm smart enough to take you on the tour that somebody else took me on, but I'm not smart enough to invent this as a method. I mean, that's just brilliant. Who thinks of these things? People that don't have video games, that's who think of them. They're bored and they have lots of time on their hands. I don't know. Unbelievable. Now, this little time as we spend on all of this, you think about yourself taking a final exam. It's like, we still got a lot of techniques to learn. Can you feel it? Can you appreciate you're going to get overwhelmed at some point? Like, I got to be careful how I ask this. We're not going to spend weeks and weeks on this stuff. And so, in the larger scheme of things, this is kind of challenging. Wow, that's a really annoying question. I'm just staring at your book right now to see like which problem should we do now. Let's do an initial value problem. Let's, on the next page, it says the same thing, but it says solve the initial value problem. And so they're actually asking us for a particular solution to this. And so, I don't know, I'm looking at 17 and thinking 17 looks kind of fun. Let's try 17. But it starts out just the same, and it says dy dx minus y over x equals x e to the x. And then it has an initial condition, but we'll worry about that in just a minute. Now notice there's one thing I'm really happy about, which is I look in front of here and that's already gone. There's nothing there. Good, that's what I needed to have happen, and that's already gone. So we're ready to go mu hunting. What is the p value that I'm taking the integral of?
1 over x.
1 over x. It's the equation in x in front of y. It doesn't include y. So it's just 1 over x. It's negative 1 over x. Now, do you agree the right side's a little terrifying over here? Ooh, that right side's terrifying. It's got x and e to the x. And so, that's not good because I can't put those together. What's the integral of negative 1 over x?
Is it the negative natural log of x?
Correct. I like your tone of voice. Like, is it negative? Not, it's like, I'm not sure, but I think this is what it is. It was a conjecture by the tone of voice that Connor used. I think it's negative. And to that end, I'll erase this, but you could pull that negative out front and it would just be the integral of 1 over x. Maybe it's easier to see there. And notice, had I written that as x to the negative 1, again, I might have screwed that up. Now, again, you might say, okay, I'm done. This is mu. But if you do that, this is pretty ugly. Do you notice you can clean this up a little bit? Do you notice that is the same thing as e to the natural log of x to the negative 1 or 1 over x? But isn't e to the natural log of junk just the junk itself? So it's 1 over x or x to the negative 1. That's the simpler multiplier here. So I'm going to pick, I don't know, that one. I'm not really sure which one's easier, but it's like, okay. And again, I find myself thinking, okay, well, I might've made a mistake through there. I'm not exactly sure. I'm not that good in integrals. There's all kinds of things I could have done wrong, but it's like, I think that's my mu. And so I'm just going to kind of blindly trust that it works. And so now I'm going to multiply both sides by it. Ooh, do you notice something wonderful just happened on the right side?
Just left
What
with
one?
e to the x.
Can you see that somebody worked really hard here to make this problem nice? You can't just stick anything on the other side you want. We got really lucky here because if this is true, then the integral of that right side, which we're going to have to take, is going to be a piece of cake, right? So that actually kind of makes me think I probably got this right since this is a book problem. But again, my next question to myself, because I don't always assume this, is, you know, is that really the product rule? Like, just come and double check, is that true? Is if I take the derivative of 1 over x, do I actually get 1 over x squared? So I'm going to think to myself here, let's see, 1 over x would be x to the -1. Its derivative is bring the -1 out front and then subtract 1 from the exponent, -1 over x squared. Huh, check. That's exactly right. It did work. So this amazing mu technique worked, and more amazingly, I didn't do anything dumb in finding it. So now I take my non-derivative terms and write the product rule before it has been taken. And the left side is the left side, which is very conveniently simplified. And so the fact that this problem writer stuck this x in front, you might have thought, that wasn't very nice of them. Why didn't they put something easier over there? Well, if they had left that x out, notice it would have been worse. Isn't that amazing? It's like somebody really put some thought into this, was nice to us. We're being spoon-fed right now. Good, because we're not that good at this. Now I'm going to integrate both sides because I'm basically home free. You always have to take an integral to solve a differential equation, and now it's time to do that. And of course, the integral of e to the x is just e to the x, and there is a plus c here. And then notice it's really important not to leave that plus c out, because we are not finished with this problem. Just watch this for a second. Let's say you just kind of forgot that, you know, because that's an easy thing to do, because it's so much less important when you actually take Calc 2 to kind of include that. So say you forgot it for a second. And so you said, okay, well, I'm done. All I have to do is multiply both sides by x. So I say y is equal to x multiplied both sides would be x e to the x. And so you're like, bam, I'm done, right? And so you say, oh, yeah, whatever, I forgot a constant. So what? Who cares? I forgot a constant. It just moves it around a little bit. But is that just the c?
It's a c times x.
Because the c is actually over here. It's actually c times x. And so it's not just a constant. It's actually something fairly significant. You see what I'm saying? So like this was the equation x e to the x, but it's also plus a line. So it's like two equations added together. This time, let's just playfully go to, let me see here. I'm going to try to do this a little different. Share screen. Sharing a different screen. Mega hits. So you are seeing the slope field thing now, is that correct? So what was our original problem? Thank you. It was, oh, notice it has to be solved. In order to type it into this, it's got to be solved for dy dx. And so I say, well, what is that? Will it be y over x, because I have to add that to the other side. I don't know if you wrote this problem down, but it was dy over dx minus y over x. So I'd have to add that to the other side. So it'd be plus y over x. And then there was an x e to the x on that side. So it'd be plus x e raised to the x power. Boom. So here is my fun direction field. Again, can you stare at that and kind of see stuff happening there? I find it hard to do that. I really am appreciative of this business. So I drag it around a little bit. So that it looks okay there. Does it have any vertical slopes in it? I'm a little bothered by what I'm seeing. Is this wonky? Is this freaking out because of the vertical slopes? I'm actually not sure. I'm not sure that isn't freaking out right here a little bit. I'm not sure. Well, let's go to Desmos. Let's see what Desmos says the answer. If we didn't screw this up, which again, we're not sure, but we're saying we got y equals x e to the x. It's not an e. And then we got plus cx. So the question is, are we getting similar looking graphs? Notice how much nicer this is and so much cleaner looking it is. Let's just see if I can reproduce that graph right there if I go back to the slope field. Do you see how something's definitely wrong here? Do you see how graphs don't do that? That's what in Calc 1 you'd call a discontinuity. It's like it's moving along and it's not smooth. The transition isn't smooth. So I'm glad this happened because notice it's kind of hard to tell. Did I get this right? I'm not really sure. I can't seem to reproduce the same exact graph.
Maybe we need to manipulate our equation so that there's not a division sign. That might help.
Good point. Very good point. Manipulate this equation, the original equation, so there's not a division sign. Because remember, when x is 0, whenever it hits x is 0, you have y over x, and that's going to make it kind of freak out. And so can you see that here when x is 0? Notice there's no lines on it, but every one of those would be vertical. So basically what's happening is whenever this hits the y-axis where x is 0, it's kind of like it explodes. It doesn't like it. And so that's kind of what I see happening. It's like everything was doing great. It was kind of curving along like this, and then it sort of hits the x-axis and then like turns into a totally different graph. And so this one's just kind of a bummer. That's kind of the issue. Let's see, is there some way to get rid of that x? The problem is I'm not sure there is. I don't know how I would get rid of it. I don't think I can make it so it isn't y over x. I mean, I could write it as yx to the -1, but I don't think that's going to change anything. So that's kind of good to see, but my overall thought is maybe this wasn't a good one to look at the graph. I mean, maybe if you will, it would have been, better had I kind of used the technique I used before, which was to just try to solve it, like take the derivative and stick it back into the original equation and all of that. I'm just going to assume in the interest of time that I didn't screw this up, since that check really didn't help. And I'm saying that only because you all watched me do it, and had I done anything dumb, you probably would have said something. Now, this problem, however, goes on to say that, no, this actually has an initial value, and it says that when x is 1, y should be e minus 1. So that's the initial value problem, which means we don't have a family of solutions. We have one particular solution. And maybe we'll go back, maybe we'll get lucky and we'll be able to go back to that graph and maybe it'll work over there in some way we can kind of tell. I don't know. So now let's get that involved. So let's see. When I stick 1 in for x, I'm supposed to get out y is e to the -1. So 1 in for x would make this just e, because x is 1. So it would be 1 times e to the 1 plus c times x. But if x is 1, so then I guess I see now that if I subtract c must be -1. So that means my particular solution to this is actually x e to the x. C is -1, that'd be minus x. So that's actually my full solution here. So let's go back to the screen and see if we can actually do that. So in Desmos, we're letting C be -1. So that's our graph right there. Again, let's just stare at this for a second. What I'm expecting is it's going to come down like this, but instead of just smoothly connecting, it's probably going to, panic and do something different on this side, but let's just see if that actually happens. How do I put this in? I think Cheyenne told us if you click on this, you can actually put your point in. So what's my point? When x was 1, y was supposed to be e minus 1. Can I get away with e minus 1? I'm not sure I can. I'm just going to whip out. So e is 2.718. If I subtract 1 from that, then isn't that 1.718?
Looks like the right side of it worked.
Yeah. So in a sense, what maybe we thought was going to happen, which is what happened, which is it was kind of like on its way down here. But again, when it hit the x-axis, it freaked out. But if I turn this off, would you agree that if you just look at these lines yourself, since this is using Euler's technique to draw this graph, if I'm cruising along right here, when it gets down here, doesn't it look like it takes off over there? I mean, isn't that, if you're just to sketch it yourself, doesn't it kind of look like what we saw here? Isn't that kind of what it looks like? I wouldn't have been able to sketch that very accurately. But that's a little disappointing, right? But I guess I would say, you know, there is some evidence that that actually checked our work. Screen mirroring thing seems to freak out. Let's see, I think we have time for one more example. Assuming we get lucky and it isn't too complicated. So I don't know. And by the way, I'm kind of picking that. I can't remember what problems I assigned, but I'm kind of picking the problems in the book that are, you know, a little on this more straightforward side. Let's see, but I would like to pick one that looks a little bit wonky. I don't know, like 21 has trig in it, so that seems terrifying. So let's try that one.
There was one with a trig substitution in 2.2 also.
So yeah, that's right. Trig substitution was there too. Okay, great. Let's see, is the pen not, why is the pen not working? Is it uncharged? So 21, I'll write this out in a second, but maybe you're looking at a book or something. That's great. If you're not, I'll write it in a second. But 22, I'm actually assigning 22 and it's got trig in it. So this is probably a good one that we're doing. So it says cosine of x times dy dx plus y times the sine of x equals 2x cosine squared of x. Man, that just seems like an awful problem. So 21 cosine of x times dy dx plus y times the sine of x equals the terrifying 2x cosine squared of x. And so again, I find myself wondering, as a teacher, were they really nice over on that right hand side? Is like something going to cancel out of there? Are they making it so that something wonderful is going to happen? So what's our pattern again? What's our first move here?
Get rid of the cosine. Divide everything
Cosine.
by it.
Okay, so here's some good things. What did they, why is this kind of nice, what they did right there?
Because you're losing one of the cosine on top in the numerator.
Yeah, so notice I'm losing one of the cosines over on the right hand side. And what's kind of nifty about this middle term here?
That turns into I think tangent or
You
something.
are correct. Yep, sine over cosine is tangent. And I remember on my open math, I posted an integral table, I posted derivative rules, I posted a trig sheet. And so, you know, it's like, oh, I forgot what sine over cosine is. Well, all that stuff you have access to for everything you do in here. So, okay, well, it looks like they were trying to be nice to us a little bit here. So that's good. And so I'm ready to go now. And I say, okay, great. I have to go get mu. And so I'm ready to go mu hunting. And mu is found by taking e and raising it to the integral of, well, tangent. Tangents are p function. I'm not going to write dx up there this time. Uh-oh, what's the integral of tangent? You say, well, I'm going to cheat and go to that integral page. Let's see. I'm just going to pull it up.
Secant squared.
No, the integral of secant squared is tangent. If this had been secant squared, I've been really happy. Since the derivative of tangent is secant squared, the integral of secant squared would be tangent. So I wish this was, you're close. What you just said was really close to true, but this isn't simple. The integral of tangent's not nice. And notice I'm looking because I don't remember. I don't know what it is. Let's see, on the sheet that I shared with you, it is number 70. The sheet that every back of the book and trig table that you find on the internet is different, but the one that I shared with you is a really good, clean looking one. It's number 70. It says the integral of tangent is negative natural log of cosine.
You can just rewrite it as sine over cosine, then use a u sub.
Nice job. As it turns out, I'm not going to go down this road, but had I left it as sine over cosine, that would have actually been that's how you figure out what the integral back when you took Calc 2, that's how you find the integral of tangent. If you substitute it back to sine over cosine and you let u be the cosine of x, wonderful things happen. So yeah, if you want to go down that road either after class or on your own to convince yourself that this is the integral, then terrific. Now again, are we done with mu? Is this the best place to leave mu? E to the negative natural log of cosine of x.
You can turn it into negative cosine x.
Yeah, notice that negative would be cosine to the -1 power. Actually, all of a sudden I'm confused. Is that? Yeah, that'd be 1 over cosine, and 1 over cosine is secant. And so e to the natural log of secant is actually just secant. So the better answer for what's mu is just secant. Multiply both sides by the secant of x. And now I find myself going, really? Again, just like every time, really? Multiply both sides by secant is going to create the product rule? You got to be kidding me. There's no way that's going to work. That's what I find myself thinking. So I do that. I say, okay, great. I'm going to multiply both sides by secant of x. And so I have dy dx times secant, and I have tangent times secant. And notice there's not much I can do with that right now. And then the other side is 2x times the cosine, also multiplied by the secant. And so the question is, did it work? Is that the product rule? What's the derivative of secant? Look on my trig cheat sheet that I shared with you, because you probably don't remember. You shouldn't have that memorized. If you do, wow. I want to use
secant x times tangent x.
Indeed, is secant tangent. The derivative of secant is secant tangent. Oh my God, I cannot believe this worked. Again, that mu thing is awesome, isn't it? Like when you're staring at this problem right here, would you have ever guessed that in a million years? Oh, I'll multiply both sides by secant. Like, how would you ever come up with that? It's just crazy. You should have chills running down your spine right now. Oh my God, I can't believe this works. And so you're saying, and by the way, what happened on the other side? What happened over there?
Cosine x, secant x cancel. Yay.
Secant is 1 over cosine, and so those cancel, and so somebody was watching out for us, because had that not happened, we would have had the integral of a really something nasty over there, right? So you got to be really careful how you create these problems. It's kind of like somebody really put some thought into this stuff, and so whoa. So you're saying if I have secant of x, not sex, come on, concentrate. The integral, the derivative of that equals just 2x on the other side. Oh, wow, this is going to be much nicer. I can't believe this is working. What a crazy technique. I take the integral of both sides. Now integrate. The verb integral. Integrate. That gets rid of the derivative on the left side. The integral of 2x is just x squared. Don't forget the c. Really important. Again, I keep saying this, but remember it's plus c on both sides. But I should collect them on the right. And now I'm done because all I have to do is divide by secant. And so y is equal to x squared over secant. And it's c over secant. That's why the c becomes so important. And of course, it's way better to realize that 1 over secant is actually cosine. So therefore, I don't have to write it as a fraction. And I get a trig function I'm more comfortable with, right? And of course, you're more than welcome to factor cosine out and say it's cosine times x squared plus c. That's of course fine too. It's like a trig function plus times a parabola. I mean, is it kind of a surprising answer? Let's see if we get lucky this time, and maybe if I go check our work. I don't know. I'm such a kind of a visual person. I want to see it on the. I want to see it in the graph. Maybe we'll get lucky this time. I don't know. Let's go check this. So the original problem was solved for dy dx. We had dy dx plus tangent of x times y, so I'd have to subtract that to the other side. So it'd be minus y times the tangent of x. And then there was a 2x cosine of x on that side, so plus 2x cosine of x. Wow, what a crazy graph that's going to be. Ooh, isn't that fun? So again, do we get lucky here? Are there vertical slopes? Notice the graph is like freaking out right there a little bit. So it's like, I don't know. I'm sort of thinking, oh, we're going to get unlucky again this time. Do you see how there appears to be something weird going on right here? You see how any place the graph isn't smooth? See how there's kind of a bump in it right there? That's kind of a, or right here, it's like it comes up and then just suddenly goes back down again. Like, yeah, this is kind of wonky. Maybe I could get it in one position, like one certain place where this doesn't happen, but it's like, this isn't working too good. One of the things we'll talk about later in class is, remember that kid's hair I showed you that had a cowlick in it? There was like one spot where it was really kind of weird. See how that's kind of happening right here? There's like some weird spots in the graph. Like we're going to talk about those later on in this class, so it's kind of fun. But it's like this is freaking out in those weird locations. Notice right here, there's like a swirl happening right there, and right here, there's also kind of a swirl. They're all kind of pointing into it. It kind of has this whirling sort of effect right there, and so I don't think the graph technique is working all that great here. I'm not satisfied that this is really going to help us check this. Let's see. I think in the interest of time, given the class is already 5 minutes over, I think I'm just going to stop just so that I can let you guys out here on time. Because again, this is an initial value problem. And then they gave me a really weird initial value. So I don't think I'm even going to kind of bother to figure it out, because they say that at pi over 4, and then they give, instead of something like 6, instead of saying something like y at pi over 4 equals 6, they say it equals negative 15 squared root 2 pi squared over 32. I mean, what a ridiculous expression that is. If I myself think, is that somehow going to make my life easier, or are they just trying to torture us? I don't know. So I am going to check this. I mean, we're out of time and we're done. I'm not going to say anything else, but I am going to go ahead and check this by taking its derivative. I'm going to try to plug it back into the original problem up here and see if that actually works. So stay if you want to watch that, but if you need to leave, go for it. Because if I have time and I'm you on a test, I'd kind of like to know I got this right. I'm very merciful, as those of you that had me before. I'm very merciful on tests. If I can read your work and I can ascertain what your mistake is, and I spend a lot of time, I'm not spending hardly any time looking at your homework. That's kind of on you, but I'm going to spend a lot of time looking at your test. And if I can read your handwriting and your work is reasonably clear and I can ascertain where you went wrong and determine it was an accidental mistake as opposed to you don't know what you're doing, you know, I'm going to be very merciful and partial credit because you watch me make dumb mistakes all the time too.
The worst part is when you can ascertain that I don't know what I'm doing.
Exactly. And I usually
Those
can.
notes are rough.
So let's see, what is y prime or dy dx? From up here, since I have to, you know, plug it in right there. So what is it? Well, I see product rule. And I don't know which form to do it in. Actually, I think I'll do it in this form. The derivative would be the derivative of cosine of x, which is negative sine of x, times the other part left alone, plus the cosine of x left alone, times the derivative of x squared plus c. That'd be 2x plus what? What do I do with c? What do I do? Well, it's a constant. Doesn't matter what it is. What's the derivative of a constant? Nothing. So there's the derivative. So now I'm going to plug this into the red equation. So if I take cosine of x and I multiply it by that derivative, negative sine of x times x squared plus c plus, well, I guess I could rewrite that, plus 2x times the cosine of x. And I add that to c cosine of x. I'm just rewriting what's written right here. Then the question is equals question mark. Will that actually equal the cosine of x? I'm not even plugging this in the right place, am I? What am I doing?
So did you solve for dy over dx?
Yeah.
Okay.
Yeah, so I took, I'm sorry, I got to stop and rethink. I think I'm doing something stupid here. So here's the derivative, right? I figured it out. There's the derivative, but then I stupidly, I think I started plugging it into the blue equation instead of the red one. So let me just think out loud for a second. So I should be plugging it into the red equation. And I did that. So then it was cosine of x times dy dx, which is all of this junk. Cosine of x plus plus 2x. Actually, I don't think I made a mistake. I think I was okay. Plus 2x cosine of x. So I've got this much of it complete now. Does that make sense? It's cosine of x times the derivative. And then it's plus y, this is where I went wrong, plus y sine of x. And then it's question mark, is that really equal to 2x cosine squared of x? You know, and I find myself thinking it's going to be a miracle if that's true, right? So that's why I put a question mark there. So then I distribute this cosine of x in. So I have negative sine of x cosine of x times x squared plus c. And then I distribute cosine of x into this and I get plus 2x cosine squared of x. That's a good sign because that's what I'm supposed to get when I'm done. Plus y sine of x. Question mark, is that equal to 2x cosine squared of x? Well, the only thing I don't have is this y. Like I need that y gone too. I need all x's. And so what was y equal to? Well, according to my, let's see, is that my derivative? Yeah, I guess it's this, isn't it? Isn't this what y is equal to? Or this, y is equal to that, either one of those. So if I throw that in there, cosine of x, I'm going to write this in red. So y is equal to cosine of x times x squared plus c. Is it working? Notice that I have minus sine of x cosine of x, x squared plus c. What do I have here? Plus sine of x, cosine of x, x squared plus c. So those cancel out, and then I have 2x cosine of x squared equals 2x cosine of x squared. Check. Actually didn't screw that up. It worked. I'm just curious. I'm gonna look at this really quick. Maybe. But if I'm just wondering what note sheet I stuck in here. Calculus, let's see, is it tests? Final exam notes. I posted this also because this will be everything we learn in this class, and there should be lots of things on there you're totally confused by, but you actually should now understand note number 1 right there. Linear first order differential equation. Why is it first order? Because it's just y prime, not y double prime. So that's dy dx plus p as a function of t. Notice I use t instead of x. So this is the p function, and then multiply both sides by mu to set it up for the product rule, where mu is equal to e to the integral of p dt or dx. Notice that's something you don't have to memorize for a test or for later on. That's what we use today. And so now you're kind of on your way to making sense of how this works. And so highly recommend, if you're not gone, highly recommend you do tonight's assignment, well, tonight, so that we start off tomorrow either with you going, wow, I got all those right, I'm doing great, I'm ready for more, let's go. Or you start off with, what questions really threw you? Anyway, just something to think about.